time to start. So it gives me great pleasure to welcome Alex back to Cornell to give a talk. So for those of you all who don't know, Alex is actually an alumnus. So he was in the computer science department where he worked with John Steinberg and has actually worked with a lot of people at Cornell and has been back a few times, even recently, for giving talks in other departments, but never in applied maths. Now, this is actually an incredibly good talk to give a sense of what Alex works on. So after leaving Cornell, he was at MSR Silicon Valley, and then after that closed down, has been at MSR New York for a long since then. And he's been working on a set of ideas connected to sort of how optimization over time relates to the underlying geometry and the constraints, how it relates to the way in which data is collected, and also how it relates to how people are reacting to this optimization, the incentives in the problems. And he's done a really beautiful set of work relating these three topics in many, many different ways. But then even more than the work, he's actually done a lot of thinking about how to just kind of encapsulate all these ideas and bring out the best in them. So he taught a couple of courses related to this topic. And the reason I know he's thought a lot is I actually taught a course related to some of these topics like last year, and while I was searching around for the best way to actually try and convey these ideas, I came upon his notes, and a large part of my course was basically just following Alex's notes. Now, luckily for us, he's then gone on to actually make a book out of this, which is released now, or
yes, it
is about to be released on these topics. So if this stuff seems exciting, Alex is around for a little bit more, you should talk to him, but definitely also check out his book. Having read it, it is really nice.
Thank you. That's nice. Okay, thanks. Great to be back. Yeah, thanks. Yeah, so I'm going to talk about adversarial bandits. With Knapsacks, I'm going to explain what it means in a couple of slides. In the meantime, it's joint work with a bunch of colleagues inside of IC, and currently used to be a lecturer, it's now at Facebook. Okay, so I'm going to start with a couple of motivating examples. So, oh yeah, I'm going to start with a bit of a background. So, generally, it's about multi-bandit problems, where, in general, you have a setup where time proceeds in rounds, and each round an algorithm chooses some action from a set of actions and receives a reward in most basic setting. We assume that this reward comes from a fixed distribution that depends on the arm, but is fixed over time, and is not known to the algorithm. And we get what's called bandit feedback. So it's like we only see the reward for the chosen action. We don't know what would have happened had we chosen some other actions. And it's like a classic model for something called explore-exploit trade-off. That is a tension between experimentation to find out new stuff about which arms are good, and kind of using this information to make optimal decisions. By the way, in case you wonder why we come to bandits, it's like one-arm bandit is a slot machine. It has one arm, it rolls your hands, it's a bandit, and you have several machines that are like your arms. Give you some payoffs, you don't know where they are. Okay, so that's bandits. And there's been like a huge amount of work in this area, maybe like a few thousand papers over a couple of decades, with like kind of a surge in the past couple of years. So anyway, this talk is going to be about like one line of work in this space. It will be about like algorithms that consume resources. And let me give you a few examples for like what that means. Right? So, say we have a dynamic pricing setting. So we have like a seller which has an inventory and is trying to sell stuff all the time and can experiment with prices. Right? So like a very, very simple model for that is like this. In each round a new customer shows up. It has some private values like value at which you would buy. It's not known to the seller. The seller offers like one item at some fixed price. take it or leave it offer. So customer accepts this offer and buys if this price is smaller than the value, and rejects it otherwise, and leaves. So and this continues until there are no more items or no more customers. You could think selling seats on a plane or on a concert or anything like that. Another example, oh yeah, and the goal is that the algorithm adjusts prices over time in order to maximize value. So one could think of a stochastic version of this thing where they have this probability of accepting a given price, and it's called something called demand distribution. And in the basic version, this thing is fixed over time and not known to the seller. So that's dynamic pricing. Another nice example to keep in mind is kind of dynamic buying in some sense instead of dynamic selling. So say you have an employer on a crowdsourcing market with many tasks and limited budget, and it just wants to hire people to do some tasks. So it's very, very simple model for that is like this. In each round, a new worker shows up, which has a private cost for doing this job, not known to the seller or to the employer. So employer offers a price, take it or leave it. A customer accepts if this price is good for him, or rejects otherwise, and that continues until you're out of workers or out of money. Right? So the goal is again adjust the price over time to maximize the number of tasks. And again, one could think of a basic stochastic version when the probability of accepting a given price is fixed over time. And it's assumed not to be known to the algorithm, and effectively it's something that you want to learn about. Another example, so sort of the breadth of this is you allocate ads over time. So you have pay-per-click ads, meaning advertiser derives value from clicks and only pays when there is a click. You got multiple advertisers with budgets. In each round, a new user shows up and platform chooses an ad and receives a signal, click or no click. And if there is a click, then the advertiser pays you something. So each advertiser's budget is effectively the maximum number of clicks that it's willing to pay for. And if budget is exceeded, then all the ads are removed. So again, the goal is to do this over time in order to maximize the number of clicks. And again, one can define a stochastic version where click probabilities are fixed over time but not known. Okay, so see, a common theme here is that explore trade, or you kind of experiment and try to do the optimal thing at the same time. Under resource constraints. So in all three examples, the algorithm keeps consuming resources. So here's a general model that kind of unifies all these examples and a bunch of others. We have D resources abstractly with some budget for each resource. In each round, the algorithm chooses an action, or let's call it an arm in brackets, and it receives an outcome, which is a vector. It consists of reward and consumption of each resource. And it goes on and on, and the algorithm stops if any resource exceeds the budget. And by the way, you could think of time as just another resource. You just consume 1 unit of this resource no matter what you do, and there's a time horizon. So it's you keep going until you're done. And this type of constraint is called knapsack constraint. It's if you remove the online aspect of it, you're just sometimes trying to fit a bunch of things into your knapsack, which is a famous knapsack problem, and banks with knapsacks. So you could think of a stochastic version of it, which is that the outcome of a given arm, which this entire vector. It comes from some distribution over outcomes, which depends on the arm, but not on the time, and it's not known. And to keep things a bit simpler, we normalize. So all rewards and consumptions are in the 0-1 interval, and also without loss of generality, we kind of normalize so that all budgets are the same. There's like one budget B, which is like one of the parameters of the problem. And basically the goal is to maximize the total reward given the constraints. Right. So let's see how all these examples fit into this model. So in dynamic pricing, action is a price. Reward is the money that you get, and consumption is that, well, if you sell, you spend an item. In dynamic procurement, like action again is a price. Reward is the task that you complete, well, that the worker completes. And consumption is that the algorithm spends money, and there is a budget of money. In the ad allocation example, well, action is one of the actions are ads. Reward is basically clicks, and consumption is the advertiser money and other components. And let's look a bit.
So when you were describing the examples earlier, you said until you're out of items or out of customers, and you are not putting the customers under consumption here right now. Is there a reason?
Oh, great question. Customers is basically time horizon.
I see. But
So
so
in each round, the customer shows up. It just
so
means
you
time
are
horizon.
separating out the time horizon. And is the time horizon known a priori to the algorithm,
Yes.
or do you want to
Yes.
stop any time?
Yes, let's say it's known to the algorithm. I'm just saying, so in all of these examples, there is a time horizon, and there's other thing.
Okay. And so the adversarial transition money is only consumption but not reward if you're Google?
Is it good?
When you're Google, the
Oh,
advertising
so
money is not also
effectively,
reward?
effectively it's both consumption and reward because like clicks means money. But you're right.
You know nothing about your opponent's distribution of values. You only learn that by playing the game. Is that
Let's
correct?
say yes. Yes. I mean, in practice, you may know something which can be modeled as some initial data that you start with or a prior, but I mean, let's kind of separate that away for now. Right, so let's see in a bit more detail how like outcome vectors map here. So in the pricing example, so if you accept your reward as this and consumption is 1, if you reject it's 0, 0. In the procurement example, it's kind of similar, but it's different. So the reward is 1 and the consumption is 2. And again, if you reject it 0, 0. If in the ad allocation, like you get clicks, and if it no click, it's, I mean, you get a reward of 1 and some budget is consumed. If no click, it's all 0. But it could be anything. And by the way, it's important that different components of the outcome vector can be correlated with one another. For example, if there is no sale, it's 0, 0. So it needs to be correlated to capture these examples. Okay, so it's a fairly general model. So not just that it captures these 3 examples, but it kind of captures a whole lot more inside each example. For example, in dynamic pricing, it could be like not selling one product, but selling multiple products with limited supply of each. In procurement, it could be like multiple types of tasks. And in ad allocation, each advertiser could have multiple budget constraints that need to be satisfied simultaneously, and there are a bunch of other applications. So it's kind of a general thing. One more piece of background is that, so we look at bandit feedback, which is that if you choose an action, you only observe the outcome of this action. There are 2 other feedback models out there which are worth mentioning. It's like what's called full feedback. So you choose an arm and you observe the outcome of all outcomes. And there is huge literature, like each of them in like learning theory world, and also in like OR and econ. And there's also a model which often goes by online algorithms. It's usually in theoretical SES literature, where, and just some OR literature, where you observe the outcomes of all actions before you need to choose your action. So in some sense, you know everything about the past, you know everything about the present, but you don't know the future. And there's also a huge literature on that one too, but like, we focus on this one, not the benefit.
When you generalize the model to multiple research constraints, so you still get one single price, but whenever the buyer, for example, picks that at that price, is it the case that two different resources, for example, get deducted from your budget? But it's a single price. It's not like the customer has multiple options to pick from. I mean, it's still
in the full generality of the model, you just have like algorithm chooses among actions, and every action leads to a reward and consumption of resources. So, like in these examples, they mean a particular thing, but from now on, it doesn't matter. Just like you choose an action, you observe some consumption of each resource. They could be consumed in weird ways.
I guess what I'm confused about is how could showing two different prices lead to two different consumptions of a single budget?
Oh, I mean, say at one price, customer buys, and the other price, the customer doesn't buy. A different consumption. It's like, you don't consume anything, there is no sale.
Right. But it's not like two decisions to buy something will lead to two different ways in which the budget is deducted.
So you could be selling multiple products, and your actions are price vectors.
Okay.
And like if you post a price vector, people can react to it in different ways. They could buy this, apples, or they can buy oranges. Okay. So there was a bunch of prior work. It started with dynamic pricing, for which there's like a lot of stuff. And like if like all these special cases were studied before, then at some point we defined this general model and kind of made up an optimal solution for it. And the weird thing that happened is there were like 3 very different algorithms that are optimal for this model and kind of cool to analyze. It's just the state of affairs. And then there was some follow-up work on like extensions to kind of different bandit setting. It doesn't really matter to this all what they are, it's just that like the problem space of different bandits is kind of multi-dimensional. You could start at the basic problem and like make it more complicated in many different realistic ways. And if you start with a basic bandits with Knapsacks problem, you may want to do the same. And that's like let's all that work. Okay, so this work is on the following topic. So all prior work was in the stochastic setting. So how about adversarial? In other words, what if the outcomes do not come from like a fixed distribution over outcomes, but instead they are chosen by an adversary? And I guess we'll look at the oblivious adversary, meaning that like the adversary can choose things arbitrarily, but it needs to make all the choices before round 1. But it's still an adversary. And another kind of annoying thing was that, like I said, there was this like bandit setting has many aspects, and ideally you want to handle many of them because in any practical setting you have like many of them at once. But somehow the way research works, you take like 1 or 2 of them and like try to handle them, and it's like already very hard. And ideally, you'd like to have kind of generic techniques that just work in many settings, or ideally like a reduction. That, if you can handle, I don't know, contextual bandits, then you can carry it to contextual bandits with knapsacks, stuff like that. So, we delivered on both of them. So, like, we have a solution for adversarial bandits with knapsacks, and we have a reduction. And so, in some sense, it's an optimal solution. explain what it means in a little bit. And like I said, it's only going to be about oblivious adversary as opposed to like adaptive adversary, which is a more devious kind of adversary that can adapt to the choices that you made so far. So a key technique happens to be a new algorithm for the stochastic problem, and it's kind of conceptually simpler than the previous algorithms, and it's kind of has this more teachable flavor, I think. And it happens to be, well, kind of optimal. It's like optimal for what I think is the main regime in some sense, and it has nice analysis. The adversarial algorithm is essentially using the same algorithm as a subroutine with a completely different analysis. Moreover, so that would give that gives guarantees and expectation, but with a huge variance. Then we have like a much more complicated algorithm, which kind of the most technically complicated in this paper. And this algorithm again uses like that algorithm, the stochastic algorithm, as a subroutine, and the adversarial analysis of that as a lemma. So it's kind of nicely builds up in one part. Okay, and this whole thing really works as a reduction from bandits to bandits with knapsacks, so it immediately leads to several extensions. Okay, so the way I'm going to do the rest of the talk is that I'll do some intuition and background, then I'll do this new stochastic algorithm in some detail, even though it's kind of a simpler part of the paper, it's kind of conceptually nice. And also kind of explains why the adversarial algorithm even makes sense. And then I'll talk a little bit about adversarial algorithm and kind of explain what it is. I won't like, try to prove anything. And I'll conclude with extensions. Okay, so first of all, I want to say a few words of like why stochastic bandits with knapsacks is a big problem. Why bandits with knapsacks is difficult even in the stochastic case, right? So one thing is, well, exploration is limited by budget that you, your ability to exploit is limited by the budget that you exhaust in exploration, which is like different from your usual bandit problem where you explore and then you know how much time you will have when you explore. Another thing, well, usually in bandits, the thing that you try to do, just kind of conceptually, is that you maximize the reward per round. And here it's really not the right goal, because well, the arm that gives you the best reward per round may be exhausting lots of resources and may be like really horrible in the long run. Now, even kind of a weirder reason is the following. In the usual bandit problem, if you knew the outcome distributions, then the best thing to do is a fixed action. Here, the best thing to do is not necessarily a fixed action. And here is a simple example. When it happens, say you have like two resources, kind of vertical one and a horizontal one, and two arms. One vertical arm that consumes only the vertical resource, and a horizontal arm that only consumes horizontal resource. Right? And say both arms give you a reward of 1. So, okay, the best fixed arm only goes in that direction or that direction, but if you could alternate, then you could get like twice as much reward. Right? Or, kind of almost equivalently, if you could randomize uniformly, then you would get almost twice as much reward. So, in other words, the best distribution over arms could be much better than the best fixed arm. Okay, so there are kind of difficulties in the stochastic setting. And yeah, I mean, that one is a contrived example, but similar examples exist in like every special case that you would care about.
Is there a ratio between the best distribution and the distribution bounded by the number of resources?
Good question. I think we definitely have examples where there are at least three. I think it's, yeah.
Yes.
Okay, but adversarial problem is even harder for a completely different reason. So the new problem that shows up in the adversarial setting is basically whether you want to spend all your resources now or you want to save them for the future. Here's like a very simple example when it happens. Say you have two arms, like one resource with a budget of like a time horizon of 2. And the arms are very, very simple. One arm is like null arm, it's not doing anything. It's not getting you any reward, not consuming anything. Arm 2, say it consumes 1 in each round. And well, in the first half time, the rewards are medium, and then they could be either low or high. So you need to decide in advance like how much budget you're going to spend in the first half time until you know what's going to happen in the second half time. And that already dooms you to like approximation ratio of 2. And like with a more careful construction, and kind of slightly more careful analysis, one can massage this like approximation ratio being at least log t. So now it's no longer about like regret minimization. In other words, it's like not about minimizing the additive term, which would be kind of decreasing over time, but it's really about approximation ratios. Yeah. Okay, so what are our benchmarks? In other words, like when we argue about how good or bad is the algorithm, what do we compare it to? Well, a standard benchmark in Bandits is the best fixed arm. The benchmark that kind of the right benchmark to focus on here is the best fixed distribution over actions, which is, I've explained, could be better. So that will be our benchmark, kind of the benchmark that we care about. Now, the benchmark that we really compete with on a technical level is essentially a linear relaxation of the best fixed distribution. And for the stochastic setting, it's kind of the best algorithm is sandwiched in between. So really, we're also competing with the best algorithm. And for the adversarial setting, the best algorithm would do much better, and we're not even trying to compete with it. It's just too far.
Thanks for the clarification on that. So when you're saying best fixed distribution, you're assuming it's probably so it's independent across time.
Yes.
Okay, that's not necessarily optimal. Or that's not the minimax optimal distribution.
Right. It's
It's intermediate.
So we get, one gets red bounds with respect to LP opt.
Sure.
Like morally, these are the same up to like
Oh, no, what I meant is you could also have a sequence of distributions over time,
Yeah.
which could be stronger.
So I agree, but since the best algorithm happens to be sandwiched in between, then you might as well think about this. But either way, for the adversarial setting, the best algorithm is really too hard to compete with. There are like lower bounds of like C over V's. It's not like logs to really see. So anyway, in short, the best algorithm is too hard. We're competing with the best distribution. And the types of yes, sir?
I feel like this is a stupid question, but why is the best algo in the adversarial setting better than in the stochastic setting? Like, shouldn't it be worse? Because what's the relationship you're assuming between the adversary?
The adversary is oblivious.
Is the stochastic setting among the set of things that the adversary can do?
Yes.
Okay. And
Like, I think this is the benchmark.
Yeah, that's the bench. I'm just saying that like competing against the best algorithm is too far. I think adversarial setting. Just like, sorry, with the best algorithm in hindsight.
I see.
It's
Okay.
like if you knew the adversary,
I see, okay.
what would be your best algorithm? Right?
Not the
Thanks.
minimization.
Thanks. So yeah, the guarantees that the type of guarantees that we're getting is the following. In the stochastic setting, it's like regret, which is the difference between this, the benchmark and the total expected reward of the algorithm. In the adversarial setting, it's the competitive ratio, which is the ratio between the opt and the total expected reward. Okay, so any questions so far? Okay. So let me talk about the algorithm, this new algorithm for the stochastic setting. It's going to be, I think it's kind of conceptual, and I have this game plan that I'm going to follow. So we start with the linear relaxation, which is that it's like I say, what would happen if all rewards and consumptions happen in expectation? So for each distribution over actions, we could define the expected reward, expected consumption, and we could say, what if we fix the distribution for all rounds and we stay within budget? And like, what's the optimal thing one could do? Okay, that's a complete linear program. It has an optimal value, and that's our measure. Okay, now just for any linear program, I could define a Lagrangian. Oh yeah, I'm sorry. And the previous work implies that like the LP value is an upper bound on the out, so we don't need to worry about it. Now we can write out a Lagrangian, just we can do it. It doesn't matter for the stock what Lagrangian is exactly, but it's a well-defined formula. But from now on, we can just think, it's a function from like primal variables and dual variables. It won't matter what it is exactly. What's important is that the dual variables here can be interpreted as a distribution of the resources.
So my question is, so I can understand this is a linear programming relaxation, but actually you are assuming so the distribution you are optimizing is actually homogeneous with respect to the time horizon. But I mean, maybe the optimum policy is not.
You're right. So, right, it's in that sense, it's not immediately clear that it's a relaxation. But formally, all we need is this, but it's not a boundary. You're right. Okay, so a Lagrangian for us is just some function from two things: the distribution over actions and the distribution of the resources. Right? And it's kind of a useful thing. We are going to define a game between two players, what will be like a primal player that chooses actions and a dual player that chooses resources. It's going to be a zero-sum game, but the payoffs are given by the Lagrangian. So it's like for primal player it's the reward, for the dual player it's cost, and the amount is given by the Lagrangian. So the useful here is why it makes sense. Is that, well, if a primal player samples action from a distribution and a dual player samples resource from distribution and we plug that in, well, so the expected, so by linearity, the expected payoff is like Lagrangian of one distribution and the other distribution. And there is this useful theorem that the value of the game corresponds to the value of the linear program. More specifically, if we have a mixed Nash for this game, then the value is the same, and like D is the optimal solution for the LP. So in some sense, like our original goal is to find the optimal solution for the LP, but it's like essentially the same as solving this game. Okay, now we can define a repeated version of this game, but we kind of do it in this roundabout way. So we think that in each round, conceptually, there is this outcome matrix, which is like a matrix over like actions and outcome vectors. So, you know, even though the algorithm does not observe all of it, but conceptually we can think of it. So it's like actions versus outcome vectors, right? And for the stochastic setting, so each of these outcome matrices is sampled from a fixed distribution. For the adversarial setting, it just means that these matrices are sampled by the adversary before round one, right? But we have these objects. And we can think of the expected outcome matrix, which is just a matrix of like expected rewards and expected consumptions. So it's like really the problem instance is defined by this expected outcome matrix. And all the setup so far is basically determined by the outcome matrix. So we can think of this Lagrangian as a function of the outcome matrix, of the expected outcome matrix. Well, okay, but you know, it's just a matrix, so let's plug in for round outcome matrices. And we get something interesting. So let's define this game where in each round, I'll have this primal player that chooses actions, dual player that chooses resources, and the payoffs are given by the Lagrangian, which is defined not with respect to the expected matrix, but with respect to the per round matrix of this time. Well, why is it interesting? I mean, we can look at the expected game. Well, expectation, the payoffs are like Lagrangians with respect to the expected matrix, which is kind of one thing that we're interested in. And moreover, this game is implementable, meaning like the feedback that we get in the Bandits for Knapsacks problem suffices to like compute the payoffs in this game. So, you know, the primal player chooses an action, dual player chooses some resource, but the feedback that we see in Bandits with Knapsacks, well, it's the consumption, it's the rewarded consumption of every resource, so we have enough data to compute the Lagrangians. Okay, so again, we want the mixed match in this, Lagrangian game because it maps back to like value of the LP that we care about. Okay, now it happens to be kind of a very standard and famous result in learning theory, which is the following, that like regardless of this Lagrangian game, if we just have a like repeated stochastic game, in other words, like a repeated game where the game matrix is zero sum and is sampled from a fixed distribution in the round. And we have like two players in this game that are implemented by like online learning algorithms. Well, with the caveat that like these online learning algorithms need to work against adaptive adversary, but still, such algorithms exist, so it's okay. So we have this theorem which we're going to build on, which is that okay, on a high level things converge to the Nash equilibrium. More specifically, if we look at the distribution of the average play of the primal player, just like we'll look at the frequencies, and we'll look at the distribution of average play of the dual player, well, they form expected Nash with well, almost. They form the Nash equilibrium and the expected game, which is what we really care about. It's not exact, it's approximate, but the slack that depends on the regret of the first algorithm and the regret of the second algorithm and second term. Oh, that should be a root. Sorry, that should be a root. Yeah. So like small-ish slack term. But you know, on the high level, things converge to the Nash. So, hence there is an algorithm, which we call Lagrangian K. So, we've got two bandit algorithms that play this repeated Lagrangian game. one algorithm chooses actions, both in this game and in the actual like bandits with knapsacks problem. The other algorithm chooses resources and receives full feedback. And I mean, it doesn't have to, but we can give it full feedback, so like, why not? There is this final step in the analysis that we need to kind of add, is that, well, the game is not gonna go until the last round. It might stop when they run out of resources. In fact, it might stop like, very soon. But it's not too bad. We still get large reward. And like, basically what's happening is that, well, we stop. What does it mean that we stop? It means that some resources spent. Well, we can write out what this approximate Nash condition means for this resource, and like write out the Lagrangian and like, you know, flag in the fact that like we spent all this resource, and like flag in the error terms, count them using standard asymmetrical qualities, and voila, comes a statement that will get larger. I mean, I'm not like showing you that in detail, but it's like literally all that's going on. So that whole thing suffices to say that like if we use kind of standard algorithms for bandit feedback and for full feedback, we can get this background, which is optimal for this problem in the regime when like both opt and d are like a constant fraction of t, which is kind of, you know, not the only regime of interest, but kind of a main regime of interest. So it's kind of good. A prior work does get better regret balance and optimal regret balance for any triple, like opt BT. So like, it does better, but at the cost of like more complicated algorithms. And also there is a general theorem. Basically, it works for any like any, you know, ALG1 and ALG2 in terms of the regrets. So it's like instead of like these terms are like provable guarantees for these two algorithms. Okay, and like
Ask a simple question. Looking at the lambdas are bounded for so you had to learn the Lagrangians.
right. So for us, the lambdas are a distribution, and like we cannot load the standard result that connects the Lagrangians to the value. We need to like, you know, derive this thing from Lagrangians. It's probably no, just we have to derive it actually. Right. So kind of putting everything together is not like super complicated, but it's kind of a little subtle, and I really like how it combines into this sort of big picture that like, you know, we switch from the original problem to linear programming using this relaxation and the fact that like we bound it off. Then we go to Lagrange game by defining Lagrange functions and like noting that like game value is the same as the LP value. Then we go from Lagrange game to like a repeated Lagrange game by, you know, invoking this learning games framework and this standard theorem. And then we have this last step where we prove that like even if we stop, we still get a large reward that kind of gets us back from the repeated game to the bandits with knapsacks, setting and do this theorem. So it's kind of a high-level picture.
How large is the integrality gap?
Excuse me?
How large is the integrality gap?
So in the stochastic setting, it's kind of on the order of root t additively, and in fact it's on the order of like root b if I'm not mistaken, like root of the budget. Okay, so that's the big picture for the stochastic setting. Now let's try to go to the adversarial setting. Well, there are like good news and bad news. Good news is that the algorithm is well defined. It didn't matter that like these game increases come from the distribution. It's still well defined. The bad news is that all analysis completely breaks down. I mean, we had this high-level picture, but like it just doesn't work. But just all steps just don't work. We need to do something completely different. Okay, so here is what is our algorithm actually. So we write out a Lagrangian, and well, it had this t, but we replace it with t0, which is now a parameter. We randomly guess it, and the semantics of this is that it's our guess for the value of opt. It's like if we knew opt, we would plug it in. If we don't, well, we don't, so we need to guess it from some exponential scale. And that's pretty much the entire algorithm. So we guess this value of t0, we shove it in, and we run the previous algorithm. That's it. And so far the intuition for this algorithm being reasonable is, hey, it used to make a lot of sense in the stochastic case. Right? Why it makes sense here is kind of unclear, but somehow it does. So let's try to see how we analyze it. Right, so first of all, we need to argue about the benchmark. So linear relaxation is not quite the linear relaxation that we had before is not quite the right thing anymore, because what if we need to stop early? Because what if we really want to spend all the budget by halftime? It means that we really want to stop early. So the way to redefine the benchmark is the following: we choose a fixed time tau. We replace the expected outcome matrix, which we don't have anymore, with the time averaged outcome matrix. Okay, now with this matrix we can just define the LP program just as we had before, but which tau should we use? It's unclear. So instead we just choose the max over all possible taus. So that's the benchmark. In other words, we replace the expected outcome matrix with the time average. We use the same LP program as we had before, and we maximize all the taus. Okay, and one can prove and it's not very hard that that is really the upper bound on the opt and adversarial set. But here it's very important that opt is the best fixed distribution over actions as opposed to the best fixed algorithm in ISA. Okay, so now there is a sort of crucial lemma about this algorithm in the adversarial setting, which says that, okay, for any given fixed stopping time, the reward is at least something. And it has kind of two cases. One is about what happens if the algorithm runs out of resources too soon. The other is what if it doesn't? So okay, we can only get the min of that. So it's in terms of this parameter and the stopping time. It's kind of the crucial step here, and I guess I won't go into it. But once we have it, then okay, optimizing over all the taus, we get this nice little bound. And once we have that, well, if our guess for T0 was right, that is, if we guessed it on the scale of opt, that is all good. We get this, ratio, this competitive ratio, and well, this algorithm is really good if and only if this was the right guess, and the guess is right, the probability essentially log t, so that's the final issue. That's all there is to it. Okay, so far so good, but I mean, that's good, that's almost the right ratio, yes.
So do you remember what the D stands for?
D?
Yeah.
The number of resources.
Oh, I see.
So it's optimal-ish ratio for, if you don't think of the dependence of resources. Log T is optimal. Okay, so it would be nice to achieve the same ratio, but with high probability, right? Now, that is a lot trickier. So what we do is essentially we start with a small guess for opt, and we increase it adaptively. Now, so okay, how do we do it? In each phase, we still run this main algorithm, Lagrange decay, with a parameter equal to this guess. So, okay, at each step we like look at the average out. We want to look at the average outcome matrix. We solve this LP. It gives us some estimate of like what the opt is. Well, if our current guess is too small, then we like increase the estimate and we go to the next phase. We like restart the algorithm. Okay, we're not quite done because like we can't really observe the average outcome matrix because we don't have full feedback. So instead we like sample uniformly a little bit and we use IPS estimates, kind of standard stuff to kind of estimate everything, and we suffer for that in regret, but kind of that works out. And so that is essentially the algorithm on like high level, and that's like about as much as I can go into. The interesting thing about the analysis is that it uses this Craig's lemma as kind of one of the key steps in the analysis. We use the stuff in the previous analysis, and it calls this, algorithm or Lagrange decay as a subroutine. Other than that, well, it's complicated. So, like, we argue that we don't spend too much budget in every phase, and then we only count on the last phase, and then we show that, okay, in the last phase, we're at 3 million. But it's kind of a technical piece of the data. Okay, so that's about what I want to say about this algorithm. Now, let me talk a little bit about extensions. Right, so, generically, we could have a primal algorithm that is not just algorithm for bandits, but it's algorithm like contextual bandits or any other like many extensions of bandits, and like it immediately translates into the algorithm for like this extension for bandits with knapsacks. The significance is that, well, no new research is needed, whereas in prior work, each such extension was, essentially a separate paper. And I mean, sometimes it gives slightly better guarantees if you do it like a separate paper, and sometimes not, but it's like, now it's like really, really simple. And for the adversarial setting, all these results are just new, but there was nothing there before. One substantial caveat is that, well, it's not just any algorithm for this for this or that extension of bandits. Like, even if we want to handle a stochastic version of things, we need an algorithm that works against adaptive adversary. And, well, such algorithms do exist for some settings, and then we can just use them, and that's it. And they don't exist for some others, so, and then we cannot use them. But, when and if somebody comes up with them, we can like automatically plug them in. So that's extension, and I guess let me talk a little bit about open questions out of this work, and I guess out of like this whole line of work. So, I mean, conceptually, our algorithm for the stochastic setting for the adversarial setting is like almost the same algorithm, right? So it seems like a very, very lingering, very, very plausible. Like, can you have like really the same algorithm that would handle both the stochastic and the adversarial version? And it would kind of answer this philosophical question that, well, what if you're like, your guarantees for the adversarial case are like really pessimistic. Why are they so pessimistic? Well, if we had this one algorithm that would handle both versions, then we could say, well, they're only pessimistic because the adversarial case is so hard. But if you're in the nice case, then they're like really good. So that would be good. Unfortunately, the adversarial stochastic algorithms are slightly different in like 2 annoying ways. One is that, well, there is this parameter, which in one case is a guess, and in other cases, like, it should be like a time horizon. More annoyingly, like the algorithm is like more or less the same, but it all starts with some notion of the outcome matrix. And for the adversarial algorithm, it's essential to have the null arm, which is basically a null, like an arm that is not doing anything. And for the stochastic setting, it was essential to have this, you know, time as a resource. So to have like a separate resource such that each arm consumes 1 unit of this resource in every round. Well, unfortunately, you cannot have both at the same time. It's just, you know, null arm cannot consume any resources, and it has to consume 1 unit of time resource. So it's like not exactly the same algorithm anymore, even though it's kind of more or less the same. So, but it seems very, very natural. And so in the kind of bandits without knapsacks, kind of a standard version of bandits, such results are known. So like there are these algorithms that achieve best of both worlds, you know, stochastic and adversarial. And moreover, when and if you have such an algorithm, you could ask kind of more nuanced questions about intermediate regimes, like when you're like not quite stochastic, but not like entirely adversarial, but something in the middle. Like say, what if it's kind of like IAB, but the adversary could come in and corrupt a few rounds. So you want the guarantees that scale nicely in the amount of corruption. And again, such results are known and are like really nice for bandits. It would be really cool to have it for bandits with knapsacks, and maybe it would be even more interesting to have them here, because for bandits it's just a matter of like getting better regret, but here it's like regret versus competitive ratios, like huge difference. A few more questions like is the following. Like our lower bounds do not rule out the possibility of having constant approximation ratio in this regime when V is a constant fraction of T. It seems that it should be impossible, but there is a gap, so it's up there. Another question, I mean, there are like a few other senses for like upper lower bounds and kind of rules. So like, can we do better for bandits with like many knapsacks? Currently the ratio is basically like D log T, but can we like get rid of T? It's okay. And yeah, if I can indulge in like, you know, shameless bit of self-promotion, like said, my bandit book just got published. It's, you know, broad and accessible introduction to what I think is like a really fascinating subject. It's, you know, teachable in some sort of way design, and it covers various connections to each one of the water. So, oh yeah, it's available on archive if you. Yeah. So that's that. Thanks.
So for stochastic bandit setting, you construct this zero-sum game, and then you say both players will just throw a learning algorithm and then let it converge to Nash. When you say converge to Nash, do you mean over time horizon the empirical distribution played is converged to Nash, or the actual play?
Right, the average play.
And that's enough for your result. You don't care if the actual play converges to Nash.
Yes.
Okay.
And there is a whole line of work about how like the last iterate is not really what we want.
Mm-hmm. Okay. Nice.
Sometimes it is like that.
Hmm?
Or sometimes that is what you want and that's not what is already so.
Right. Yeah.
It's both of us.
Chair, one, this may be slightly more technical, but the way you selected your team, couldn't you have just selected a random horizon and then pretended to play up to that horizon? So you were doing a doubling of horizons. Instead of that, if you just
Unclear. It's just like the way it was useful to think about it for our analysis was to think of this parameter as like an estimate of opt, not an estimate of time. So not an estimate of the optimal stopping time.
It's a minimax system, so you're trying to figure out what's the worst case that the adversary can do to you.
I mean, yes. I mean, it's entirely possible that that would work too. It's just like we did it in a different way. And like philosophically, I don't understand why it has to be this way, not the other way. It's part of it could be that we just don't understand the problem in the right way. So,
So I guess I'm familiar with results where if players are told no regret algorithms, it converges to a correlated colloquium, but what about this makes it converge to Nash?
oh, it's in zero-sum games.
It's
they
in
converge to
zero-sum
Nash.
games,
It's
okay.
like positive zero-sum
It is,
Nash.
okay, right.
I'll send it. Yeah. It's zero-sum games.
Okay, so we have refreshments next door. Let's thank Alex.